It's amazing how fast our brains can process things like recognizing a face in just a fraction of a second. It really makes you appreciate the power of our senses.
It really does. And that's exactly what we're diving into today. This incredible world of sensation and perception.
Exactly. And, we've got this really in-depth chapter to work with. So our mission today is to give you a really clear and engaging understanding of these fundamental processes in psychology.
Absolutely. We're going to break down the core principles of how we experience the world, starting with the difference between sensation and perception.
Right. Because they're not the same thing.
Exactly. And then we'll get into thresholds. What can we detect? What can't we detect? And how do our senses adapt?
Oh, and how our expectations and the context we're in shape what we perceive. It's a big one.
Huge. Then we'll take a deep dive into each sense, starting with vision. How light becomes images, the workings of the eye, color, depth, motion, all that.
Plus how our brains manage to make a stable picture even when everything's constantly changing.
Right. Then we'll move on to the non-visual senses. Hearing, touch, pain, taste, smell, body position, movement, and we'll even touch on ESP.
So yeah, buckle up for a detailed journey through our senses, and we'll make sure to connect it back to your everyday life. Sound good?
Sounds great. Let's start with the basics. What is the difference between sensation and perception?
Well, the chapter actually kicks off with this really interesting case about Heather Sellers, who has face blindness. Her vision is fine, she sees everything normally, but her brain doesn't process faces the same way.
Right, so her sensation, the way your eyes take in light, is totally normal.
Right. It's her perception, the way her brain interprets that information is different. She might recognize someone by their voice or how they walk, but not by their face.
It's almost like trying to pick out one specific penguin from a whole bunch of penguins that all look the same.
Yeah, great analogy. And this really highlights the difference between bottom-up and top-down processing.
Exactly. Think of it like building with Legos.
Hmm.
Sensation is like getting all the individual bricks, the raw data coming in from your senses to your brain. It's bottom up.
Okay, I'm with you.
Perception is more like looking at the finished Lego castle.
I see. So your brain is actively building, organizing, and interpreting based on what it already knows, its expectations, and the context.
Exactly. It's top-down processing. And figure 6.1 in the chapter actually shows this interplay between sensation and perception with these ambiguous images where you might see different things depending on how your brain decides to group the lines and shapes.
Right. It's not just about taking in information. It's about making sense of it.
Exactly.
So how does that sensory information even get to the brain?
Well, that happens through a process called transduction, which is basically like the body's translator.
Okay, translator, tell me more.
It converts one form of energy into another.
Okay, so like light energy for sight becomes neural impulses that the brain can understand.
Exactly.
Yeah.
Or sound waves for hearing. And this happens in 3 basic steps that are the same for all of our senses.
All right, lay them on me.
First, we receive the sensory stimulation usually through special receptor cells that are designed to pick up specific types of energy. Then, that stimulation is transformed into neural impulses. Those are the electrical and chemical signals our brain uses.
Got it. So like those receptor cells are picking up the light, sound, smells, whatever, and turning them into brain language.
Precisely. And then third, those neural impulses are sent off to the brain to be processed.
Makes sense. And there's a whole field called psychophysics that studies the link between physical characteristics of stimuli and our psychological experience of them.
Right, so like how the intensity of a sound wave relates to how loud we perceive it to be.
That's cool. And, we're constantly surrounded by tons of energy, but we only really pick up on a tiny bit of it.
It's true, we're bombarded with radio waves, X-rays, all sorts of stuff, but our senses just can't detect them. It's like they're tuned to a specific channel.
So that brings us to thresholds. What are absolute and difference thresholds all about?
Great question. An absolute threshold is the bare minimum amount of stimulation we need to detect a specific stimulus half the time.
Okay, half the time.
Right. Whether it's light, sound, taste, smell, or touch. Like imagine seeing a candle flame 30 miles away in complete darkness, or feeling a bee's wing brush your cheek.
Wow, that's pretty incredible.
Yeah.
Or how about smelling a single drop of perfume in a 3-room apartment?
Exactly. And Gustav Fechner did a lot of research on this. Figure 6.2 actually shows how a hearing specialist might test your absolute threshold for different tones.
So it's not like we suddenly go from not hearing something to hearing it. It's more gradual, right?
Right. It's a point where we can barely detect it half the time.
Okay, I get it. And what about telling the difference between two things?
Ah, that's where the difference threshold comes in. It's also called the just noticeable difference, or JAN.
Jane, okay.
Yeah. It's the smallest difference between two stimuli that we can detect 50% of the time. And what's interesting is that this difference isn't fixed. It actually changes depending on the intensity of the original stimulus.
So like if you're listening to music really quietly and turn it up a tiny bit, you'll notice.
Exactly. But if it's already blasting, you might not notice that same increase.
And that's Weber's law, right?
You got it. Ernst Weber figured out that to notice a difference, two stimuli have to differ by a certain percentage, not a set amount. And that percentage changes depending on what you're sensing.
Okay, so for light, it's about an 8% change to notice a difference in brightness. For weight, it's about 2%.
And for musical tones, it's a tiny 0.3%. Think about that tiny difference in pitch that musicians and sound engineers work with. That's Weber's law in action.
Wow, that's amazing.
Mm-hmm.
It's all about the relationship between the change and the original stimulus. Our brains are so finely attuned to that.
They really are.
So what happens when a stimulus just stays the same for a while?
That's when sensory adaptation comes into play. Like when you walk into a room and smell fresh baked cookies, at first it's strong, but then you get used to it and barely notice it anymore.
Oh yeah, totally.
It's because our nerve cells actually fire less frequently when exposed to a constant stimulus. As neuroscientist David Hubal said, the brain is interested in things that change. It is not interested in things that stay the same.
Makes sense. We need to pay attention to new information, not stuff that's always there. And the example in the chapter of the stabilized retinal image, where an image held perfectly still on your retina fades away, really shows that, doesn't it?
It does. And you know, sensory adaptation, while it might seem like a drawback, it's actually really useful.
Oh yeah, I can see that.
It helps us ignore unimportant things and focus on what's new and potentially important, like how we tune out the hum of the refrigerator until it suddenly stops.
Or how about the way phone notifications grab our attention? They're new and different.
Exactly. It even affects how we adapt to facial expressions, which can influence how we see later expressions. Our senses are primed for novelty.
So we've talked about how our senses take in the world, but our perceptions are also shaped by what's going on inside our heads, like our expectations.
Absolutely. And that's where perceptual set comes in. It's like a mental predisposition to perceive one thing and not another.
Like that famous image that can be seen as either a young woman or an old woman. Depending on what you're expecting to see, you might perceive it differently.
Exactly. Your expectations filter how your brain interprets what you see.
And that Loch Ness Monster photo is another great example. If you believe in Nessie, you're more likely to see the monster. But if you're skeptical, you might just see a log.
Right. And the chapter has some fun examples of how this works with sounds, too. Like trying to understand someone with a thick accent. If you're expecting to hear certain words, you're more likely to hear them even if they're not pronounced exactly right.
Oh yeah, like that example where people heard cheer up as gear up in an aviation context, or how the context can make you hear stuffy nose as stuffy nose.
Exactly. It even affects how we perceive our own speech. There's this study where people listened to recordings of their own voices, but slightly altered, and they still thought they were hearing themselves perfectly.
Wow, that's crazy.
Yeah.
Like Thoreau said, we hear and apprehend only what we already half know.
That's a great quote. And, you know, our expectations even affect taste. Remember that study where kids thought French fries tasted better when served in a McDonald's bag?
Oh yeah, even though they were the exact same fries.
Or the one where people reacted differently to beer with vinegar depending on whether they knew about the vinegar beforehand.
That's wild.
And this all ties into the concept of schemas.
Schemas.
Yes, schemas. They're like mental frameworks that help us organize and make sense of new information. They're based on our experiences and play a huge role in top-down processing.
Okay, so like if you have a schema for what a dog looks like, you can easily identify a new breed of dog you've never seen before.
Exactly. But schemas can also lead to biases. Like that study where people perceived a baby as bigger and stronger when they thought it was a boy named David compared to a girl named Diana.
Wow, just because of their expectations.
Precisely.
And speaking of shaping perceptions, the chapter also talks about how context, motivation, and emotions all play a role.
It's true, they all interact. The same sensory input can be interpreted totally differently depending on the context. Like imagine someone crossing the street in front of you. If you're a pedestrian, you might be annoyed. But if you're driving, you might be scared.
Yeah, that makes sense. And then there's that study where people holding a gun were more likely to think other people were also armed. It's like their own state influenced how they perceived the situation.
It's a powerful example. And those classic examples, like eel is on the wagon, show how surrounding words can change what we hear in an ambiguous phrase. Our cultural background also influences how we see things. There's a figure in the chapter, figure 6.9, that shows how people from different cultures interpret a visual illusion differently.
It's amazing how much context matters.
It really does. And our motivations and emotions are just as powerful.
Oh yeah, like when you're really hungry and suddenly every restaurant sign seems to jump out at you.
Exactly. Motivation can make things we want seem closer. Hills look steeper when you're tired, and there's even research showing that baseball players perceive the ball as bigger when they're on a hitting streak.
So it's almost like our desires and emotions are literally changing how we see the world.
In a way, yes. And it works both ways. Research has shown that just seeing a target as bigger can improve your performance. Like baseball player George Scott said, "When I'm hitting well, the ball looks like a grapefruit."
That's a great quote. So it's not just our physical state that matters, it's our mental state too.
Absolutely. And emotions definitely influence our perceptions. Sad music can make us interpret words more negatively. Feeling supported can make challenges seem less daunting. And anger can make us perceive neutral objects as threats.
Like mistaking a hairbrush for a weapon.
Exactly. Even subtle cues, like seeing a frowning face for a split second, can make us perceive neutral faces as less likable.
Wow, that's crazy.
Emotions also color our social perceptions, like how someone might experience solitary confinement or how we view our relationships depending on our emotional state.
So it's really clear that perception is a two-way street. It's not just what's out there, it's also what's going on inside us.
Absolutely. It's a combination of both.
So let's dive into the specific senses, starting with vision. It's probably our most dominant sense.
It is. And it all starts with light. Our eyes are constantly taking in light energy, and through transduction, they convert it into neural messages that our brain then turns into the experience of sight.
But then light itself doesn't have color, right? It's just energy.
That's right. Figure 6.12 shows the electromagnetic spectrum, and visible light is just a tiny sliver of it. Different animals can actually see different parts of the spectrum, like bees can see ultraviolet light, which is invisible to us.
That's interesting. So what makes light look different colors to us?
It all comes down to the wave nature of light, which is shown in figure 6.13. The wavelength of a light wave, which is the distance between the peaks, determines the hue, which we experience as color.
So short wavelengths are bluish colors, and longer wavelengths are reddish colors.
Exactly. And the amplitude or height of the wave determines the intensity, which we perceive as brightness.
Okay, so the light comes into our eyes, and our eyes have some pretty amazing structures to focus that light.
They do. It starts with the cornea, the clear outer layer that does most of the focusing.
Right.
Then the light passes through the pupil, which is the hole in the center of the iris, the colored part of your eye.
Ah, the iris. That's what gives us our eye color.
Exactly. And the pupil can get bigger or smaller to control how much light gets in. Behind the pupil is the lens, which fine-tunes the focus of the light onto the retina.
And the retina is where the magic happens, right?
It is. The retina is at the back of the eye, and it's packed with special receptor cells that convert the light into neural signals.
So it's like the camera sensor of the eye.
Perfect analogy. And those signals are then sent through the optic nerve to the brain, which puts it all together into an upright image.
Wow, that's pretty amazing.
It is. And within the retina, we have two types of photoreceptor cells, rods and cones.
Rods and cones, yeah, I've heard of those.
They have different jobs. Cones are concentrated in the fovea, which is the central part of the retina, and they're responsible for sharp, detailed vision and color.
So like when you're reading or looking at something closely, you're using your cones.
Exactly. And they work best in bright light. Rods, on the other hand, are more sensitive to light and allow us to see in dim conditions.
But they don't see color, right?
Right. They mainly see in shades of gray and are also responsible for our peripheral vision. Table 6.1 in the chapter gives a good overview of the differences between rods and cones.
And there's this cool visual illusion in figure 6.17 that shows how rods and cones work differently.
Ah, the disappearing dots illusion.
Yeah, when you stare at the center dot, the surrounding dots seem to disappear because your rods are more sensitive to light changes in your peripheral vision.
It's a great demonstration.
And all those signals from the rods and cones travel through the optic nerve to the brain.
Right. The optic nerve is like a bundle of almost 1 million nerve fibers carrying all that information.
But there's that one spot where the optic nerve leaves the eye where there are no receptor cells.
The blind spot.
Yeah.
Yeah.
Figure 6.16 shows it pretty clearly. We don't usually notice it because our brain fills in the missing information.
Right. It's like a little magic trick our brain does.
I love that.
And when we go from bright light to dim light, our pupils get bigger to let in more light, and our rods become more sensitive. That's dark adaptation.
So that's why it takes a few minutes to see clearly when you go from outside into a dark room.
Exactly. Figure 6.18 shows the whole pathway from the retina through the optic nerve to the thalamus, and then finally to the visual cortex in the back of the brain.
Wow, it's quite a journey.
It is. And it's a great example of how our brain actively constructs our visual experience.
And even simple things like seeing light when you rub your eyes. It's because that pressure stimulates the retinal cells, and your brain interprets it as light.
It's true. Our brain is always trying to make sense of the signals it receives.
So how do we see color?
Well, color is actually a mental construction. It's not inherent in objects themselves.
So we
Like Isaac Newton said, the light rays are not colored. Different wavelengths of light stimulate different combinations of those cone cells in our retina, and our brain interprets those patterns as different colors.
Okay, so it's not like objects are giving off colored light. It's our brain that's assigning the color.
Exactly. And the Young-Helmholtz trichromatic theory explains how we see a whole spectrum of colors using just 3 types of cones: red, green, and blue.
It's like mixing paint, but with light.
Kind of, yeah. But this theory didn't explain everything about color vision, like after images.
After images.
Yeah, like if you stare at a green image for a while and then look at a white surface, you'll see a red after image.
Oh yeah, I've done that before.
That's where Ewald Hering's opponent process theory comes in.
Okay, what's that all about?
It says that we have 3 pairs of opposing color processes: red, green, yellow, blue, and black, white.
Opposing.
Yeah, so if one color in a pair is stimulated, the other is inhibited. So if you stare at something green, your green receptors get tired, and when you look away, the red receptors rebound and create that red after image.
That makes sense. The flag demonstration in figure 6.20 shows that really well.
It does. So basically, we use both theories to explain color vision: the trichromatic theory at the level of the cones, and then the opponent process theory in the brain.
It's like a 2-step process.
Exactly. And some people have color blindness, which is often a problem with the red or green cones, and it's usually more common in men.
So they might see the world in shades of gray or only be able to see certain colors.
Right. It's like having a limited color palette.
And even dogs have a kind of color blindness.
Yeah.
Dichromatic vision.
It's true. Their color world is much more limited than ours.
So we've talked about how light enters the eye, how the retina converts it into signals, and how those signals travel to the brain. But how does the brain actually make sense of all that to create images?
Well, that's where feature detection comes in.
Feature detection.
Yes. David Hubel and Torsten Wiesel won a Nobel Prize for their research on this. They discovered that we have specific neurons in our visual cortex called feature detectors.
And what do those do?
They respond to very specific features of a scene, like edges, lines, angles, and movement. They did these amazing experiments with cats where they recorded the activity of individual brain cells while showing the cats different visual stimuli.
So like one cell might fire when it sees a vertical line, but not a horizontal line.
Exactly. And these feature detectors then feed information to more complex groups of cells called supercell clusters that respond to even more complex shapes and patterns.
And some of these supercell clusters are specifically for recognizing faces, right?
That's right. The fusiform face area is a region in the temporal lobe that's super important for face recognition.
That's fascinating.
It is. Damage to this area can cause face blindness, while stimulating it can make people see distorted faces. fMRI studies have shown that different parts of the brain light up when we look at faces compared to other objects.
And the brain doesn't process all this information one piece at a time. It does it all at once, right?
Exactly. That's called parallel processing. Our brain divides the scene into different aspects like motion, form, depth, and color, and processes them all simultaneously.
That's amazing.
Figure 6.22 shows a simplified diagram of this.
And that leads to the binding problem, right? How does the brain combine all that separate information into a single unified image?
That's right. It's still a bit of a mystery, but it highlights how complex and dynamic visual processing really is.
So the brain is not just passively recording what it sees, it's actively constructing the visual world.
Absolutely. And the Gestalt psychologists really emphasize this idea. They argued that the brain has an innate tendency to organize sensory information into meaningful wholes.
And one of their key ideas is figure and ground.
Right. Figure and ground is our ability to separate objects, the figure, from their background, the ground.
Like words on a page. The words are the figure, and the paper is the ground.
Exactly. And sometimes the figure and ground can reverse, like in that classic vase faces illusion shown in figure 6.25. What you see as the figure can change depending on how you focus your attention.
And this applies to other senses too, right? Like at a party, you can focus on one conversation while the other sounds fade into the background.
Absolutely. It's a fundamental principle of perception.
And then there are the Gestalt grouping principles, the ways we organize visual elements into groups.
Right, like proximity, where we group things that are close together, continuity, where we see smooth, continuous patterns, and closure, where we fill in gaps to see complete objects.
Those make sense. They help us make sense of the world quickly. But sometimes they can lead to illusions, like that impossible doghouse in figure 6.26.
It's true. Our brain's desire for order and completeness can sometimes trick us.
And speaking of illusions, how do we perceive depth? Our eyes only see in 2 dimensions, but we experience the world in 3D.
Depth perception is a pretty amazing feat. The visual cliff experiment shown in figure 6.27 showed that even babies have a sense of depth.
And we use both binocular and monocular cues to judge distance, right?
Got it. Binocular cues rely on having 2 eyes. The main one is retinal disparity, which is the slight difference between the images each eye sees. The greater the disparity, the closer the object.
So our brain is comparing those 2 slightly different images to calculate depth.
Exactly. That's how 3D movies work, too. They exaggerate the disparity to create that immersive 3D effect.
Cool. And what about monocular cues?
Those are cues that each eye can use on its own.
Like when one object blocks another, we know the one in front is closer.
Right, that's interposition. Other monocular cues include linear perspective, relative size, relative height, light and shadow, and relative motion. Figure 6.29 shows some examples.
So we've got a whole toolbox of cues to help us judge depth.
We do. And depth perception is crucial for navigating the world and interacting with objects.
Absolutely. Now, what about motion perception? How do we see things moving?
Well, our brain perceives motion by detecting changes in the position of an object's image on the retina. If the image is getting smaller, we assume it's moving away. If it's getting bigger, it's coming towards us.
But this can be tricky sometimes, especially for kids, which is why it's important to be extra careful around moving vehicles.
Absolutely. And we also have these interesting illusions of motion, like the fact that large objects seem to move slower than small ones, even if they're traveling at the same speed.
Yeah, like a jumbo jet seems to glide through the air while a car zipping along the highway looks much faster.
Exactly. There's also stroboscopic motion, which is the illusion of movement created by rapidly flashing a series of still images.
Like flipbooks and old school animation.
Precisely. And then there's the phi phenomenon, where 2 stationary lights blinking on and off in sequence create the illusion of a single moving light.
Like those flashing arrows on road signs.
Exactly. Our brain loves to perceive motion even when it's not really there.
It's pretty cool how easily we can be fooled sometimes.
It is. But these illusions also reveal a lot about how our visual system works.
That's a good point. Now, despite all these changes in lighting and angles, we still perceive objects as having stable properties.
You're talking about perceptual constancy. It's our ability to see objects as unchanging in color, brightness, shape, and size, even though the sensory information we receive is constantly changing.
Like a white piece of paper still looks white even under different colored lights.
Exactly. That's color constancy. Our brain takes into account the surrounding lighting conditions to adjust our perception of color.
And brightness constancy is similar, right?
Right. A black object still looks black even in bright sunlight, even though it's reflecting more light.
And we also have shape constancy. We know a door is rectangular even when it's open, and the image on our retina is a trapezoid.
Exactly. Figure 6.33 shows that.
And size constancy, where we know a car is still a full-size car even when it's far away and looks tiny.
Right. Our brain combines information about distance and retinal image size to keep our perception stable.
That's amazing. But sometimes our assumptions about distance can lead to illusions, like the moon illusion.
Yes, where the moon looks bigger on the horizon. It's because we unconsciously perceive the horizon as being farther away, which makes the moon look bigger.
But if you block out the surrounding landscape and just look at the moon, it appears smaller.
It's a classic example of how context can influence our perceptions.
So we're not just passively seeing the world, we're actively constructing it based on our expectations and assumptions.
Exactly. And that leads to the big question. How much of perception is innate, and how much is learned? The nature versus nurture debate.
It's a classic debate. Some philosophers like Kant believed we're born with certain ways of perceiving the world, while others like Locke argued that our minds are blank slates at birth.
And research on restored vision, sensory restriction, and perceptual adaptation has given us some clues.
So what have we learned from people who were born blind and then had their sight restored later in life?
These cases are really fascinating. It seems like some basic visual abilities like figure ground separation and color perception might be innate.
But they often struggle to recognize objects by sight that they know by touch, right?
That's right. It suggests that visual experience is crucial for learning to interpret and recognize visual forms.
And studies with animals raised in restricted visual environments have shown similar things.
Yes. Like Hubel and Weissel's experiments with kittens raised only seeing vertical or horizontal lines. They later had trouble perceiving the lines they hadn't been exposed to.
So it's like their brains didn't develop the necessary neural pathways.
Exactly. And there's a critical period for this development. The younger you are, the more adaptable your brain is.
Like the example of Mike May, who regained his sight after decades of blindness. He could see motion and learn to navigate, but struggled with recognizing faces.
Right. It shows that our brains are most adaptable early in life, but they can still change and adapt later on.
And perceptual adaptation is a great example of that. It's our ability to adjust to changes in sensory input.
Like when you get new glasses and everything looks weird at first, but then your brain quickly adapts.
Or that experiment where people wore glasses that shifted their vision, and they learned to function perfectly fine even with that distorted view.
And when they took the glasses off, they had to readjust again. It shows how flexible our perceptual systems are.
And then there's George Stratton's crazy experiment where he wore inverting goggles for 8 days.
Yeah, he flipped his world upside down.
It was hard at first, but he eventually adapted and could even navigate his surroundings.
It's amazing. These experiments really highlight the power of experience to shape our perceptions.
So it's both nature and nurture. We're born with certain capabilities, but experience is crucial for developing them.
Absolutely. It's an ongoing interplay.
So now let's shift gears and talk about the non-visual senses, which are just as important as vision.
They are. Hearing, touch, taste, smell, and our sense of body position are all essential for interacting with the world.
And sometimes we take them for granted until we lose one of them.
That's true, like hearing loss, which can have a huge impact on someone's life.
So let's start with hearing, which is also called audition.
Okay. We hear best in the range of the human voice, which makes sense evolutionarily.
Right. We need to be able to communicate with each other.
Exactly. And our brains are incredibly good at processing subtle variations in sound and doing it very quickly.
So how does hearing actually work? What's the stimulus for hearing?
Sound waves. They're vibrations that travel through the air, kind of like ripples in a pond.
Okay.
And those sound waves have two key properties, amplitude and frequency.
And those determine what we hear.
Exactly. Amplitude is the height of the wave, which determines the loudness of a sound.
So a taller wave means a louder sound.
Right. And frequency is how many waves pass a point in a given time, and it determines the pitch of the sound.
So a high frequency means a high-pitched sound, like a whistle.
Exactly. And a low frequency means a low-pitched sound like a bass drum. Figure 6.34 shows how amplitude and frequency relate to loudness and pitch.
So the sound waves enter our ear, and what happens next?
Well, the ear is a pretty complex organ. It has three main parts: the outer ear, the middle ear, and the inner ear.
And they all work together to translate those sound waves into something our brain can understand.
Precisely. The outer ear funnels the sound waves into the ear canal. At the end of the ear canal is the eardrum, which vibrates when the sound waves hit it.
Like a drum.
Exactly. And those vibrations are then passed on to three tiny bones in the middle ear: the hammer, anvil, and stirrup.
Those names are so cool.
They are, and they amplify those vibrations and pass them on to the cochlea, which is in the inner ear. Yeah, it's a spiral-shaped, fluid-filled tube with tiny hair cells lining it.
Hair cells.
Yeah, those vibrations cause the fluid in the cochlea to move, which bends those hair cells, and that triggers neural impulses that are sent to the brain via the auditory nerve.
Wow, it's like a chain reaction.
It is. And those signals eventually reach the auditory cortex in the temporal lobe, where they're interpreted as sound.
It's incredible how many steps are involved in just hearing a sound.
It is. And sometimes things can go wrong along the way, leading to hearing loss.
Like damage to those tiny bones or the hair cells.
Exactly. There's conduction hearing loss, where there's damage to the mechanical system that transmits the sound waves.
Like if the eardrum is punctured or the bones in the middle ear are damaged.
Right. And then there's sensorineural hearing loss, which is also called nerve deafness, where there's damage to the hair cells or the auditory nerve.
And that can